Good afternoon, class. Today we're going to be looking at our first section involving logarithms, and that's not the right assignment. Of course, I get a white error label. So let me come back over here. We're looking at logarithms, and I want to remind you of a few of the properties we used the last time. We had that zero exponent property, and we said that a non-zero base to the zero power is equal to 1. Oh, and by the way, the reason these exponent properties are important is because a logarithm is just a fancy way of expressing an exponent. So, the logarithm properties, what we were doing the last time, will be important because it's just a fancy way of expressing an exponent. And we had that negative exponent definition. A base to a negative exponent is just the same thing as 1 over the base to a positive exponent. That'll be important. We'll use this one today. I don't know if we'll use this one, so we generalized this statement and said that if you have a fraction to a negative exponent, you take the reciprocal, which means you flip it and make the exponent positive. That's just a generalization of this statement here. B to the negative n, well, what's the reciprocal of b? 1 over b, and you change the exponent so it's positive. And there's the fractional exponent properties that we saw the last time. Remember, an exponent of 1/2 is the same thing just as a square root. And in general, an exponent of 1 over n is the same thing as an nth root. And when we were doing those last problems in the assignment, I said that when you run into a radical, you're going to need to rewrite it using an exponent. I said add that to your bag of tricks, and that would follow us into the logarithms discussion. So remember, when we run into a radical, we're going to have to write it as an exponent. Now, suppose you have a rational exponent and the numerator isn't 1. 1 over n is the nth root. Suppose it's a over n, then that thing right there, the denominator, is the index on the radical. The numerator is the power that's on that thing under the radical. And that will be important for number 1, I think number 2 in the homework today. But here goes logarithms. But I'm going to define, before I state the definition of a logarithmic function, I think I'm going to remind you of the definition of an exponential function. Remember, logarithms are just a fancy way of expressing exponents. So we're going to assume that when you see that letter B, it's representing a positive number and that it's not equal to 1. Instead of using the function notation for this definition, I'm going to write it just using y instead of f of x. For an exponential function, we said that that was any function that can be written in the form y equals b to the x. What's important is that the variable is in the exponent position. That's what makes it exponential. That x right there is the variable. There's a variable in the exponent. I think I wrote that out in words the last time. Exponential function, you can spot them because the variable's in the exponent position. Now, the logarithmic function. This is the only time I use cursive. I just think it looks better if I use cursive for the log notation. log is the shorthand notation for logarithm. Log base b of x is equal to y. I think we use purple. Means, I said a logarithm is just another way of expressing an exponent. This statement means that base, the subscript b, raised to the power on the other side. So b to the y is equal to x. B to the y is equal to x. This b here is called the base, some terminology. Just like that b is called the base of the exponent, the thing that's being raised to the power, that subscript is called the base of the logarithm. The thing that follows the log notation is called the argument. And all logarithms must have subscripts except for two special logarithms. There are two logarithms that don't require those subscripts. So there are two special logarithms. And these logarithms, this notation was denoted before modern equation editors that make things so easy to type. But back in the olden days, it was really a hassle to type those subscripts. Think about it. You've seen those. You may have seen the old-fashioned typewriters in movies where they're rolling the thing with the paper and stuff. They couldn't choose the font size. They couldn't, we'll make this the subscript smaller than all the other writing. That didn't exist. That technology didn't exist. So they had two special logarithms that didn't require subscripts. The first one is called the common log, and its base is 10. If you had the common log base 10 of x, what they did for ease of notation, and back then there weren't calculators either, so it wasn't easy to do all this exponentiation. So 10 was the most common logarithm used because 10 to the power is easier to calculate. If it's integer exponents, you're either moving the decimal point to the right or moving it to the left. So if the subscript was a 10, they decided they would just drop that notation and denote it log x. If you see log with no subscript, you assume that's a base 10. The second logarithm that doesn't require a subscript is the natural logarithm. The last time we talked about the natural exponential during the class, and we said it was an irrational number and non-repeating, non-terminating decimal, so we needed a symbol to represent it. The decimal approximation is 2.718, but we use a lowercase letter e to represent that. If you have log base e of x, and the natural logarithm is extremely important in scientific calculations, and so they needed a special notation for that. Well, log was already used, and you always want the log notation to begin with the letter L. So what they did was they decided they'd reverse these initials. The natural log is denoted with an ln(x). This is not an I. No logarithm notations start with an I. I'll get so many emails from students. I typed in the right answer and I was marked wrong. Well, odds favor, you're using either a capital I, which looks like an L, but is it the same? Or, let's see, what's the other thing? I've seen people use ones, a 1N or an IN there. No, that'll be counted wrong. We'll discuss that more as we go through punching in answers today. And whether you realize it or not, these two statements up here are extremely important. Maybe this statement that I wrote right here would look better if I wrote it with the X on the left-hand side. Remember, equality is reflexive, so the left side equals the right side. I could just write it as the right side equaling the left side. I have a point to what I'm doing here. Look at this statement. For an exponential function, y equals b to the x. For a logarithmic function, x equals b to the y. Look at those statements. What's happened to x and y? This reminds me of inverse functions, which we did over, well over a week ago. Was it 9 days ago? Didn't we say inverse functions reverse the x's and y's? Let's see, where is it? Let's see. Inverse functions. No. There. Let's see, where was it? We were talking about one-to-one. Inverse functions, what do? They swap x and y. An inverse swaps x and y. Instead of a y, we have an x. Instead of an x, we have a y. So this is a classic case of inverse functions. Exponential functions and logarithmic functions are inverses. That means if they're performed consecutively, f composed with g or g composed with f, everything's going to cancel out except for whatever the original variable is. I'll just say x. I'll write it like this. I'm going to write exponential and logarithmic functions are inverses. If you look through a lot of algebra books the way I do, you'll notice they all go in about the same order. They all go about the same order. When we're looking at exponential and logarithmic functions, before you can do that, they have to discuss inverse functions. Then they have to discuss exponential functions before they discuss logarithms. And then finally they discuss logarithms, because exponential and logarithmic functions are inverses. That means if they're performed consecutively in either order, they cancel each other out. So we have two properties involving inverse functions. Let's see. I'm going to write it log base b of b to the x. This thing right here is a direct result of the definition. Remember this thing over here. Base to the power on the other side is equal to the argument. Base to the power on the other side is equal to the argument. B to what power will give you b to the x? What exponent b to what power will give you b to the x? It should be obvious. Not y, just x, whatever that thing is there. If the logarithmic function to the base b and the exponential function to the base b are performed consecutively, they cancel each other out, and the order doesn't matter. That means if this base b were written first, and then the log base b of x, they would still cancel each other out. The exponential and logarithmic functions to the base b are inverses. It is a direct result of the definition and the way the x's and y's are reversed. I think we need to see some examples though, because I think that once you see some examples, it'll look less intimidating. Here I have one. I'm going to make up one. One that'll use, we're just going to evaluate this logarithm. Let's find log base 5 of 25. And there's my blue box right here. Base to the power on the other side is equal to the argument. 5 to what power will give you 25? Here's what we want to know. 5 to what power is equal to 25? A logarithm is just a fancy way of expressing an exponent. What power do you have to put on 5 to get 25? 2. Log base 5 of 25 is 2. What about, okay, I'll make up one more. The common log of 1,000. When you see that LOG notation and there's no subscript, what do you assume it's going to be? 10. That's saying 10, here's what you're trying to figure out. 10 to what power is equal to 1,000? 10 to what power gives you 1,000? 10 squared is what? 100. So it's not 2. No, 10 to the 10th. That would have 10 zeros on it, wouldn't it? That would be, let's see, 10 billion? So no. 10 to what power will give you 1,000? 3, right. 10 cubed is equal to 3. It's just another way of expressing an exponent. Base to the power on the other side is equal to the argument. Okay, let's look. I hope I haven't been timed out. Number 1. Well, you know, before we do this one, I have another example. I'm going to make up another one. Log base 7 of 1. Here's my blue box. I'll tell you right now, this involves properties of exponents from the last class. 7 to what power will give you 1? 7 to what power? I think I heard it. Will give you a 1. Good. That's that zero exponent property. 7 to the 0 power is equal to 1. It doesn't matter what that base were. If it were a log base 3, the log of 1 is always going to be 0. But now, let's go back to that problem we were going to start with. Number 1. This is number 1. X equals log base 2 of 1 over 16. The instructions say to solve the logarithmic equation. What I'm going to do is use the fact that exponentials and logarithmics are inverses to try to cancel out that log notation. I'm going to try to use the fact that exponentials and logarithmics are inverses. In the problem that we wrote down, it said log base 2. So we need a base of 2 right here to cancel out all that stuff. I'm going to get us started. What I need here, here's what I'm thinking to myself. Right there, I need 2 to a power. Because if I had 2 to a power, I could cancel out the log base 2 of 2. But I'll get us started. I know how to write 16 as 2 to a power. Sixteen is the same thing as 2 to the 4th. So I have 1 over 2 to the 4th. And I need to get rid of that 1 over. I just need 2 to a power. So we have log base 2 of 2. What can I do to 2 to the 4th to get rid of that 1 over? We had a property. I think I'll just look at this page I have right here. We had a property from the last time. I think we're going backwards, aren't we? We have 1 over 2 to the 4th. 1 over 2 to the 4th. We can drop the 1 over, but what do we have to do to the exponent? Add on a negative. So to get rid of that 1 over, we'll pick up a negative 4. And once you have the base of the logarithm equaling the base of the exponent, those things are inverse functions. They cancel each other out, and the only thing we're left with is negative 4. When solving these equations, try to get the same base, but whatever the base of the logarithm is, you need to write the argument using that same base. So this is number 1, negative 4. Now the next one is going to require that bag of tricks, one of those tricks I told you to add to your bag of tricks. In the last homework assignment, this is number 2, x equals log, is it another base 2? Yes. Log base 2 of the 4th root of 8. Let's look at those properties involving radicals that I wrote up the last time. Where is it? Here it is. Let me switch over. Look at this statement right here. We're going to go in the opposite direction. Well, I guess we could just look at it right here. We said that that denominator will be the index. So for number, where is it? Goodness, I didn't know we've written so much the last time. Log base 2. We need it, whatever that base is, we need that as the base of an exponent. We need a 2 there. Because it's a radical, we're going to rewrite the radical using a fractional exponent. So we put the fraction bar. Remember I said that index will become the denominator. So that 4, that 4th root, the denominator is 4. The numerator is the power itself. So 2 to what power will give you 8? You're thinking to yourself, you're trying to figure out what the numerator is. 2 to what power will give you 8? 2 times 2 is 4. Times 2 is 8, so it's 2 cubed. So the numerator is 3. 2 cubed is 8. That denominator, 4, is the same thing as that 4th root. And that's the hard work. rewriting that 4th root of 8 as 2 to a power. Because once you do that, what's about to happen to log base 2 of 2? They cancel out, and what are you left with? Just 3/4, correct. And you say, well, suppose this had been something like a 7, and that were a 2. Can you write 7 as a power of 2? No. And they know that. We'll see another way. If this method is impossible, there'll be another way that we can handle these equations. But for these here, you have to be able to get the same base in the logarithm and the same base in the argument. Oh, did I type in 3/4? Any questions there? 3/4. Now, if you remember those properties I stated a moment ago, you should be able to tell me the answer to number 3 without any work. Number 3. X equals 3 to the log base 3 of 11. Okay. The base of the exponent equals the base of the logarithm. They're performed consecutively, so they're going to cancel out, leaving you just 11. I agree. That's why this statement, that these two statements here that I wrote are significant. If the base of the logarithm equals the base of the exponent, they will cancel each other out, leaving you whatever the argument of the logarithm was. And you say to yourself, well, suppose these bases aren't equal. They will be equal because you'll be the one deciding on the base. You'll be deciding what base to use here. Well, you're going to use whatever base is in the logarithm to illustrate number 4. You'll see what I mean when I say you're going to decide on which base to use. Oh, wait. I forgot to type in 11. Okay. Number 4. Let me write this problem down. Log base 5 of x is equal to 3. We're trying to solve for x. A logarithm is a fancy way of expressing a blank. I said it a moment ago. A logarithm is just a fancy way of expressing an, what did we do the day before this? Exponent. A logarithm is an exponent. So what you're going to do, notice there's something different here. In the first 3 problems, the x was by itself. And so you got the same base, you were able to get the same base as the logarithm. Here, the x is part of the argument. The trick we'll do when we run into problems like this, and we'll see more like this on in the next homework assignment. I think this is only one like that today, but if you have your variable in the argument, you treat everything there like it's a power. The last time we said, if the base is equal, for an exponential equation, if the base is equal, you can drop the base, we'd get the same base on both sides, then we drop the base and set the exponents equal. If the bases are equal, then the powers have to be equal. We're going backwards. We have the powers that are equal. Now we're going to make the bases equal. What would cancel out a log base 5? An exponent base 5. That's what I mean when I said you'd be choosing which base to use. You use the base that appears with the logarithm. Then 5 to the log base 5 cancels out. What are we left with on the left side? Just the x equals, this looks funny, but it's saying 5 cubed. 5 times 5 times 5. 5 times 5 times 5 is that 125? Any questions there? So far, not too bad, right? Okay, so I'll come over here and 125. Now, I need to do some talking about. I said earlier that a logarithm is just a fancy way of expressing an exponent, and I want to state, just like exponents have properties, I want to state three important properties of logarithms. First of all, the product rule of logarithms. The product rule says log base b of m times n is equal to log base b of m plus log base b of n. There's no review material in this assignment. It's all new material, and a lot of this, the rest of the assignment is going to be involving these three rules of logarithms. The product rule says if the argument's being multiplied, you can split it up by adding the individual logarithms. If the argument's multiplied, you add the individual logarithms. Now, I didn't have to state this property of exponents the last time, but here's the product rule of exponents. The product rule of exponents says if you have b to the n, I'll say m, times b to the n, b to the m times b to the n. If you have repeated bases being multiplied, what can you do to those powers? If you want to write it as a single power, I think I heard it. Atom, m plus n. If the bases are multiplied, you can add the exponents to get it written just as a single power. Well, that's sort of similar to what we just saw with the there's a strange similarity here, isn't there? The arguments are multiplied, you add the logarithms. The bases are multiplied, you add the powers. Well, remember I said a logarithm is just a fancy way of expressing an exponent. So there should be a similarity. Next, we have the quotient rule of logarithms. First property, the product rule. The second property, the quotient rule. If you have log base b of m divided by n, quotient means division. Suppose you have division taking place inside the argument of the logarithm. I bet y'all can figure this out. Using your logic skills, if the arguments are being multiplied, you add the individual logarithms. If the argument's being divided, what do you think you're going to do? You're going to subtract log base b of m minus log base b of n. If the arguments are multiplied, you add the logarithms. If the arguments are divided, you subtract the logarithms. There's a quotient rule of exponents that you use all the time. It's the cancellation property. It's what lets you cancel common factors in a numerator and a denominator. The quotient rule of exponents says if you have b to the m divided by b to the n like Nancy, you can rewrite that as b to d. What do you do to these exponents? Say you have x to the 7th all over x cubed. How many x's are you going to have left over? Just 4. You cancel 3 above, 3 below, 7 minus 3. That's the cancellation property that we use. So likewise, if you have bases, the same base being divided to write it as a single power, you subtract the exponents. The only reason I'm mentioning this property is because it's so similar to the quotient rule of logarithms. Bases being divided, you subtract the exponents. Arguments being divided, you subtract the logarithms. And the last one is our power rule of logarithms. We used the power rule of logarithms the last time, and I don't see it listed, the power rule of exponents. I don't see it listed here on my little list of exponent properties. I'm going to go ahead and state it. I didn't call it by name, I don't believe, but we stated it the last time. Where was it? Let's see. Hold on. I just love having this. It involves power. There it is. The power rule of exponents. Power of exponents. Power rule. I was looking. I got that lecture done the last time. I never got it done in only 61 minutes. It would take 75 minutes or longer. And I was wondering, what did I do differently that we got through so fast? Well, I guess that's it. I skipped the word rule, the power rule of exponents. It says if you have a base raised to a power raised to a power. Power raised to power, what do? You multiply. Here's the power rule of logarithms. The power rule of logarithms. The power rule of logarithms says if you have log base b of the argument m raised to the n power. People consider this a bizarre property, but to me it makes perfect sense because what did I say a logarithm is? It's just an exponent. So you have an exponent raised to another exponent. You have a power raised to a power. What do? You multiply. It lets you pick up that exponent there, move it down as a factor or a coefficient, however you want to think of it, n times log base b of m. If the exponent is applied to the entire argument, you can pick that exponent up and move it down as a logarithm because you have a power raised to a power, so you multiply. The rest of this, almost the entire remaining problems, at least the next, maybe not 15, at least the next dozen problems are going to be using these three properties of logarithms. Now some terminology. To expand a logarithm means to write one logarithm as a sum or difference of multiple logarithms. Means to write one logarithm as a sum and or difference in most cases both, of multiple logarithms. I guess that makes sense, the terminology. You're expanding logarithms, you're taking one logarithm and making it bigger. I suppose that terminology makes sense. What we're going to do to expand logarithms, I'm going to go through each individual step for this first example, and it's going to be a messy one. Then we're going to try to look at, see if we can see a pattern. Our goal will be to expand the logarithms in as few steps as possible. In most cases, one. If there's radicals, we'll add on a second step, because when you see a radical, you have to rewrite it as what? It's in our bag of tricks. If you see a radical, you're going to have to rewrite it as, and if it's a square root, cube root, fourth root, what have you, you're going to have to rewrite it as an exponent. It's already a root. You're going to write it as an exponent. So, you know something, rather than looking at the ones they have there, I'm going to make up one. I'm going to say expand. And what you're going to be doing is looking for a pattern. If you don't see the pattern, then I'll just have to help you see it. Let's say log. This is going to be messy. How about we use a common log? So since I'm making the problem up myself, that way we won't have to keep writing the little subscripts. Let's say we have the common log of, we have a fraction. Let's say we have the square root of x times a cubed, and in the bottom we have a, let's say, z to the fourth and a w to the fifth.
Can you put that down?
Oh, thank you. Thank you. When you run into a logarithm containing a radical, you must first rewrite that radical as an exponent. What exponent is the same thing as a square root? 1/2. So we have log, here's my fraction bar, we have an x to the 1/2 on top, and an a cubed on top. On the bottom, we still have that z to the fourth and w to the fifth. I don't see an operation between the x and the a, or the z and the w, which means we assume it's multiplication. The first thing we can do, keep in mind, I'm breaking this up into steps, justifying it with each property, but hopefully you'll notice a pattern. Once we're through with this, we're going to discuss a pattern that'll help you just skip to the final expansion without showing all of these steps. First thing I'm going to do, I'm going to use the quotient rule of logarithms. The quotient rule of logarithms says if you have a fraction, you can subtract the individual logarithms. The log of the numerator minus the log of the denominator. So I'm going to write this as the log of the numerator. The numerator is x to the 1/2 times a cubed minus, that fraction bar is being replaced with that minus, the log of the denominator. When expanding a logarithm, the first thing you do, if you have a fraction, you can split it up as a difference. Now let's look inside the arguments of the individual logarithms. We said that's x to the 1/2 times a cubed. Well, that's a product. The product rule of logarithms says if you have a product in there, you can add the individual logarithms. So I'm going to rewrite, first of all, I'm going to write this first logarithm as the log of x to the 1/2 plus, that times is being replaced with this plus the log of a cubed. The log of the product is being written as the sum of the two individual logarithms. Now, I'm going to enclose, I'm going to enclose these two logarithms in parentheses, and I'm going to draw a little brace saying these two logarithms came about from that first logarithm. We have a minus. We can do the same thing with the second logarithm. The z and w are being multiplied, so we can write it as the log of z to the 4th. Log of z to the 4th. Plus, those things are being multiplied, so we'll put a plus. The log of w to the 5th. Oops. I was writing my arguments in black to make them stand out better. We started by using the quotient rule. Now we've used the product rule on both of these logarithms. The last thing will be the power rule, but notice something. This first set of parentheses, it's unnecessary. You'll notice there's nothing there in front to distribute. It's an unnecessary set of parentheses. The second set, though, there's a problem. There's a minus in front of those parentheses. That means that minus is going to have to be distributed here and here. The first set is unnecessary, so I think I can convert it all just to log of x to the 1/2 plus log of a cubed. But now I'm going to distribute the minus there and there to give me a minus and a minus. So I'll have a minus log z to the 4th log w to the 5th. We used the quotient rule. We used the product rule. We've distributed the minus. We can finally use the power rule. You can only use that power rule if the exponent is being applied to the entire argument. Notice you can't bring down the 1/2 at this point because that 1/2 isn't being applied to the a cubed. The power rule is generally the last property you'll use. Bring down the 1/2. So you have a 1/2 log x plus 3 log a minus, what are we going to do with this 4? Bring it down as a coefficient, so a minus 4 log z minus, what are we going to do with the 5? Bring it down, a 5 log w. There's the final expansion. And you say, well, that looks worse than what we had. Well, not if we were trying to differentiate this, but if we had a multivariable logarithmic function and we were trying to differentiate it. From a calculus point of view, the expanded form is much, much, much more desirable. You have to notice some patterns here. We don't want to have to go through this for every problem, showing every step. Did y'all follow what we did? Here was the pattern that we used. or the process, I should say. Process to expand. I'm reluctant to write this down because I'm not going to go through this process again. We first of all use quotient rule. Then which rule to be used? To go from here to here. We took the product and wrote it as a sum. So is that the product rule? Then we did something with the minuses. We distributed the minus. And the last thing we did was which property? The power rule. And if you look through view and example, that's what they'll be doing on these expansions. But I claim at this point, at this one right here, if you understand what's happening, you're going to be able to go from this form here, get rid of, rewrite, if there's a radical, rewrite it. But then you should be able to go to your final answer. How many logarithms do we have in our final expansion? 4. Well, let's see. How do we come up with these 4? How many distinct factors do we have on top here? X was 1 and A was 1, so that's 2. What about down here? So we had 2 more, so there are 4. So each logarithm has a distinct factor. Okay, we had 1, 2, 3, 4 factors. So 1, 2, 3, 4 logarithms. Some of these logarithms had pluses. I don't see a sign there, so you assume it's what? Positive. Some of them had positives in front. Some of them had minuses in front. How did we decide on that? Look at this problem. Look back at the original problem. Remember, the minuses came about because of that minus there. Why did we have that minus there? Where were the z and w located? On the denominator. So the arguments that started off in the bottom will have minuses in front of their logarithms. Dale, you are frowning.
I'm just trying to absorb it.
Oh, okay. The arguments that came from the denominator had minuses. The arguments that came from the numerator had positives, okay. What about these coefficients? Where did the coefficients come from?
The exponents.
The exponents. The exponents became the coefficients. Let's see if you follow this, okay? We're going to expand. I think I'm going to use ln this time, natural log, just because, so imagine if we had little subscripts floating around there in that messiness. So let's just, for these initial problems, let's say the natural log of a to the 7th, b to the 1/4,
What is the line again?
natural log, log base e. And we'll see that more in the homework. It will probably be using your ln key on your calculator, okay? I mean, as we get further into the homework, the last few problems, I think. And so it's just a logarithm, log base e. For our purposes, I could have written log base 50. It would still have the same expansion. It's just easier notation if I'm going to make up one. And let's say we have a w cubed and a c to the 5th. How many logarithms will we have in the expansion? I made up one with 4 logarithms. We have 2 distinct factors on top, 1, 2, 2 distinct factors on bottom, 3, 4. So we're going to need 4 logarithms. 1, skip some space, 2, 3, and 4. Let's put their arguments. We're trying to go to a final answer like this. We're trying to combine the product rule, quotient rule, and power rule all in a single step. Some of these logarithms are going to have pluses in front. Some of them are going to have minuses. This logarithm will have a positive or a negative. This one, I think I'll put blue positive. What about this one? Okay. Well, wait a minute. We better write in the argument. I should have written in the argument. So I'll get us started. The first factor was A. The second factor is B. The third factor is W. The fourth factor is C. Oh, goodness. So we said that these first two are going to be positive because A and B are where? At the top. Now the next two, what sign will we have in front of this logarithm? Minus, and here, another minus. Where is that 7 going to go? That's going to go in front. That'll be the coefficient of the first logarithm. What about the 1/4? In front of the second logarithm, here, 3. And don't have much room. Tell me what I'm going to have to write here, real small.
5.
A 5. So 7 ln A plus 1/4 ln B minus 3 ln W minus 5 ln C. Suppose the argument didn't have any fraction bars. Suppose everything was just multiplied. Then you wouldn't expect to see any minuses. Another important thing. We can split up products and quotients. We cannot split up addition and subtraction. I left this thing blank here for a reason. Note, log base B, if you have a plus or minus in the argument, that can't be split up. If you have a plus or minus in the argument of the original problem, you're going to have a plus or minus in the argument of your final answer. I'll say, cannot be separated. You can only split up products, quotients, and powers. Sums and differences. If you have an A plus B in the argument of a logarithm in the original problem, you're going to have that same A plus B in the argument of your final answer. I think we're ready to look at some of the homework. And I don't know why is Chrome flashing here. I wonder why it's flashing like this. Oh, I don't want to move. For the very first one, they've made it easy on us. It's multiplication. Oh, by the way, sometimes instructions say to expand it. Other times they say use the properties to rewrite it. You have one logarithm, they want you to rewrite it as multiple logarithms. So let's see. Let me write this problem down. And then we're going to try our one-step process for expanding. Log base 7, and we have a fraction. We have a square root of x times, look at this, you have to look real closely. Do you see that 3? It's right there over the hook. That's saying it's a cube root of y. It's not saying you're taking the square root of x and cubing it. That 3 is the index on the following radical. That's a cube root of y. On the bottom we have a w to the 7th times a square root of z. Notice that 7 is not right there over the hook. It's to the left of that hook. Looking closely, you can tell that 7 is on W. It's not saying a 7th root. So you have to look at these things closely. Any questions there? The 3 is an index, so a cube root of y. The W is not right there over that hook. It's to the left. So that 7 is on the W. So what sort of radical is this? This last one. No index shows, so it's a square root. We have to rewrite the problem using exponents. So we have log base 7. He just now said a square root of x. A square root of x is the same thing as x to the what exponent is the same? Oh, wait a minute. Thanks for reminding me to switch to my paper. The square root of x is the same thing as x to the 1/2. The cube root of y is the same thing as y to what power? 1/3. W to the 7th, that doesn't have to be changed. That's just W to the 7th. And the square root of z is the same thing as z to the 1/2. How many distinct factors do we have on top? 2. How many distinct factors do we have on bottom? 2. The w and z. That means we need a total of how many logarithms? 4. We're going to need 4 log notations. So 1, 2, 3, 4. Let's fill in the arguments. What's going to be the argument of that first logarithm? X. The argument of the next one? Y. W and Z. Why don't we put in the coefficients, and then the last thing we'll do is put in the signs. Will this first argument, this first logarithm have a coefficient? And if so, what is it? 1/2, I agree. The second logarithm, will it have a coefficient? If so, what is it? 1/3, the exponent on the y. What about this third logarithm? Will it have a coefficient? If so, what is it? 7, I agree. Here, 1/2, the coefficient on, the exponent on z becomes the coefficient. And now the signs. Notice x and y are both up top. So what sign do we have here? We assume a positive. Here, that's a plus because y is on top. What about w? It's on the bottom. So what sign are we going to have? A minus. Once you convert to minuses, you can never go back to pluses. You've done everything on top. Everything else is on the bottom. So what do you have here? Another minus. Correct. If you get the hang of this, you'll be able to impress your friends. So there, A, B, C, or D. I think it has to be C. That's the only one that has a positive 1/2. Yeah. Check. Okay, we're going to expand. This is number 6, and we're going to have to type in the answer. So I think it'll be the first time we've used the subscript key, the subscript hot button, I should say. We want to expand log base B of x cubed y all over z to the 6th. At least there's no radicals. If there are radicals, we have that additional step where we have to rewrite it using exponents. I think we can go to the final answer. How many distinct factors do we have? Let's start on top. 2 on the bottom. Just 1. 2 plus 1. How many logarithms are we going to need? 3. We're going to need 3 logarithms. Log base b, and log base b. What's the argument of the first logarithm? X. Argument of the second logarithm?
Can you switch back?
Oh, thanks. Goodness. Okay, so we have 3 log base b's. X is the argument of the first logarithm. The argument of the second logarithm. Y. The argument of the third logarithm. Z. Let's put in the coefficients and signs as we go across. The first logarithm, do we have a coefficient? If so, what is it? 3, positive or negative? Positive because x is on top. The next one, do we have a coefficient? If so, what is it? No, because there's no exponent on the y, so we don't have a coefficient. What's the sign connecting these things, though? It's a positive because y is still up on top. Z. Do we have a coefficient? If so, what is it? 6 plus or minus? Minus because z is on the bottom. Any questions there? So, oh, you have it written down? Yes. Okay. And so we start typing. 3. Notice what I'm doing. I always said don't use capital letters. You use lowercase letter L-O. But what happens when I type the G? If you're typing it correctly, it's now bolded, so you can clearly tell that's not 31. That's 3 times L-O-G. We need a subscript. You go down here to the subscript button, the gray box with the little blue box there, that lowers it down, and you type the B. But you don't type the X next. Before you type that X, you have to right arrow out of the subscript position to type the X. Then plus. I've said all along, you should never have to use a space sign. You should never have to use capital letters. If you're using capital letters, you are doing something wrong. So here we go. L-O-G. Shift down arrow is the, what do y'all do? Do y'all use the hot button or the shift up arrow and shift down arrow?
I click the button.
Okay, well, then I'll click the button too. Okay, get out, type the Y, and what was the next sign? Minus, and we had a coefficient of 6. L-O-G, wait a minute, L-O-G, wait a minute, what's happened? I typed the notation, look, it didn't bold.
It looks like they were still in the exponent.
My problem is I typed an I. This is the thing that I have so many people messaging about. They type the right thing, and I'll tell you right now, you do it on a test, and they count it wrong, I will not give partial credit for it. Okay? do not use capital letters. The only letter that looks like that little vertical mark is a lowercase letter L. Logarithm, the word logarithm begins with what letter? L. Even natural logarithms, logarithm, it begins with an L. So you type an L, not an I. And then you check your answer, and sure enough, we got it right. Oh, I like this one. I like one thing about it. It's an log. Do you see a subscript? No, that's a common logarithm. It'll be quicker to type. You won't have to type in that subscript. This is number 7. The common log of, look at that, that's the 8th root of A over B. We're expanding the logarithm. There's only one correct first step. When you have a logarithm involving a radical, you must rewrite the radical using what? An exponent. The 8th root is the same thing as what power? 1/8, that's right. The 8th root is the same thing as the exponent 1 over 8. Our pattern that we use makes the assumption that you don't have a huge quantity raised to a power. If you have a huge quantity raised to a power, you're going to have to simplify that. A over B to the 1/8, that means you have A to the 1/8 and B to the 1/8. So rewrite it. Apply that 1/8 to both the A and the B. I know my mother's at home dying, but I'm ashamed to say how much I enjoy doing these logarithms.
Oh my gosh.
Right? I feel bad when I think to myself, I'm actually enjoying myself, okay? I feel guilty about that, but how many distinct logarithms will we need in the expansion? 2. There's only one distinct factor on top, one distinct factor on bottom. So we have a log and a log. Why don't we fill it in going across? I think y'all are ready for that. That'll help me space the stuff better, okay? So, do we have a coefficient here? If so, what is it? 1/8. Argument, A.
Or minus.
Okay, we're going down to the denominator, so a minus. Do we have a coefficient here? If so, what is it? 1/8. Argument, B. I guess we had that third step here where I took the quantity raised to the 1/8 and wrote the numerator to the 1/8 and the denominator to the 1/8. But otherwise, it was still pretty short. I'll be short typing because we don't have to hassle with the subscripts. Has everyone gotten that written down before I switch over? Okay. 1/8. Get out of that denominator. Here we go. It's L-O, and look what happens when I type that G. There's no subscript. I type an A minus 1/8. Get out of the denominator. Log, B. 1/8 Any questions there? Hey, look at this. We're getting instructor tips. Never type capital letters or hit the space key. If you're typing it in, I guess it means the answer, incorrectly, each log will automatically bold. Logarithms always begin with a lowercase letter, and he wrote it out, E-L, L, not a capital I. They begin with a lowercase letter L. When I say he wrote that in, who did that for these problems? My brother. He was the one that went in and had it set to do that. Oh, we have to write, let's see, let's do this one. Number 8. Let me write it down. Log base f of, there's a fraction. We have the square root of s, the square root of s, t to the 5th, all over, is that an r cubed? Square root of s.
Oh, the 2 is not under.
Is that t to the 5th?
That's t to the 5th. I'm going to have to do something before I start expanding. What will I do? That square root, I'm going to rewrite that as s to the 1/2. So we have s to the 1/2, t to the 5th, all over r cubed. How many logarithms will we need in our expansion? 3. Let's write the first one. Will the first logarithm have a coefficient? If so, what is it? It'll have a 1/2, then log base f, argument s, plus or minus? Plus, because we're still on top. Well, we have this next logarithm. Will it have a coefficient? If so, what is it? 5 log base f, argument t, plus or minus? Minus, because we're going to the bottom. Coefficient 3 log base f, argument r. Any questions there? And we'll have to use that subscript button when we're typing in our basis, those f's. Here goes. 1/2, get out of the denominator, log, subscript f, get out of the subscript s, and then we said that was a plus 5 log base f, get out of the subscript for t, minus 3 log subscript f, and our argument was an r. Is that what I wanted to type? Yes, it is. Remember I said a plus or minus in the argument cannot be separated. That x squared plus 6, you're going to have x squared plus 6 in your final answer. It's not going to be split up. X plus 6. That's going to appear together in your final answer. You cannot split up pluses and minuses. They count as one distinct factor. Oh, I like this one. At least it's an ln. It's easier to type. Let me write this down. We have the natural log of,
Are those brackets?
let's see, it's brackets, yes. You can put parentheses. I guess they thought brackets looked better. Notice something. Is this a square root or is it a cube root? Look closely. Is that 3 sitting over the hook? No, so that's just a square root. So we have an x cubed times the square root of x squared plus 6. So we have an x cubed times a square root of x squared plus 6. And on the bottom, we have that x plus 6 squared. They put brackets. They could have just as easily typed parentheses. They could have just put nothing. They could have put nothing. That would have been perfectly fine not to have any symbols or grouping around that. The only time symbols of grouping are absolutely required is if the argument is in the form m plus or minus n. Here we have multiplication and division. How many distinct logarithms will we need? How many distinct factors do we have? We have x cubed, so x is one factor. The square root, that's all one factor. You can't split up the x squared plus 6. This x plus 6, that's all one factor. You can't split up plus or minuses. So with that in mind, how many logarithms are we going to need? 3. Hey, I should have done something about that square root. Oh, wait a minute. I'm still pointing and y'all can't see what I'm pointing at. That thing right there. What am I going to have to do before I do anything else? So we have ln. That's an x cubed. The square root of x squared plus 6 is the same thing as x squared plus 6 to the 1/2. Oh, what does that say? Oh, what did I do? I don't use Outlook on here. I never even set it up. I guess I'm logged into my account. So the square root of x squared plus 6, that's an x squared plus 6 to the 1/2. And I still have that x plus 6 quantity squared. As I said, those brackets aren't necessary. The only time they're necessary is if your logarithm, the argument is just m plus n or m minus n. You'll see what I mean in a moment. How many distinct LNs do you think we need? How many distinct factors does this argument have? 3. Okay. The first argument is that x. So we have ln x. Do we have a coefficient here? 3. Positive or negative? Positive, we assume, because that x is on top. Plus or minus? Plus. Well, we have a coefficient.
1/2.
We'll have that 1/2. And then ln, our argument will be x squared plus 6. And when you're typing it in, you have to enclose it in parentheses. Without the parentheses, we assume you're just taking the ln of x squared. And that's not right. You're taking the ln of that entire quantity. The only time parentheses are absolutely required is when your argument is in the form m plus or minus n. Nothing else. We're ready for the third logarithm. Is it going to be a plus or a minus? A minus. ln. Oops, wait. I didn't ask y'all. Minus. Will I have a coefficient?
Yes.
What is it? 2. ln. X plus 6. Is this okay? Is this what I'm going to type? No, the x plus 6 must be enclosed in parentheses. You cannot split up a sum or difference. That sum, in this case we have two sums, they have to stay together, they have to be enclosed in parentheses to indicate that they're together. Any questions there? Okay. So we have a 3. Notice I'm about to type it ln. Notice what's going to happen. ln, it bolded, x plus, we have a 1/2. Get out of that denominator, ln. We have to type the parentheses, x superscript square plus 6. I have to close it. And then minus, maybe I'm just lying to y'all. Do you think it's possible I've made a mistake? Maybe I don't need that parentheses. Let's see. Let's type x plus 6 like that. Let's see if that's correct. Will they count it correct without the parentheses? Certainly not. And the little error message isn't that helpful. It doesn't say, hey, look at what needs parentheses. It just reminds you of those 3 basic properties. You come back and close the x plus 6 in parentheses, and then any questions? Like my brother says, in algebra we always do something one way, and then what do? We go in reverse. What do you think? Taking multiple logarithms and writing them as a single logarithm is called condensing. Y'all think y'all can go backwards? Let's see, I'm going to write that out. Here we've been taking single logarithms and writing them as multiple logarithms. I'll say condensing logarithms is the process of writing multiple logarithms as a single logarithm. The instructions will either say condense the logarithms, or they may just say write as a single logarithm. So we're going to be going backwards. Just remember, if the logarithm is preceded by a minus, where does the argument go? If the logarithm is preceded by a minus, it goes in the denominator. Where does the coefficient go? It becomes exponents. If the logarithm has pluses, or the arguments in the denominator, x squared plus 6 and x, there, positive 3 and a positive 1/2. Where do they go? Up on top, okay? So with that in mind, think about foiling and then reverse foil factoring. Foiling is pretty easy, right? But when you start going backwards, that's what gets messy, trying to get the right combination to get you back to the original polynomial. Y'all know what I'm talking about? It's easier to FOIL than to factor. Fortunately, for expanding and condensing, it's about the same amount of work. It's not like this is going to be a lot harder. So number 10, log base 10 of 9 minus log base 10 of 7. Write as a single logarithm. I believe this notation, log base 10, the common logarithm, I believe that within the next 20 years, that notation will just be completely gone. With modern equation editors, why do we not need to type the 10? We can type any other subscript, so why do we need this notation? I think they're just going to do away with it. And what I've noticed, I think that you're going to have to type the 10. If they show the subscript 10, you're going to have to type it. I'll write down my log notation, log base 10. Question, will I need a fraction bar in my argument? Yes. What's telling you yes? That minus right here. The fact that we have a minus, that says we're going to have a fraction. Okay? Where's 9 going to go? Top or bottom? Top, because I don't see a sign there, so we assume positive. So 9's on top. Where's the 7 going to go? The only other place, the bottom, because it's preceded by a minus. Any questions there before I type in the answer? No? Okay. So log. I'm going to see if they'll accept it without the 10. 9 over 7. Oh, no, what did I just done? That's not what I was doing. Log, L-O-G of, I guess I'd have to put in the fraction bar. Let's see. 9 over 7. Let's see if they accept it. No. If they show the 10, the programmers are going to make you type that subscript of 10. Now let's check. Yes. Now when you do the same problem, it probably won't have a 10 there. There'll be a log base 7 or log base 5. And this programmer, whoever programmed this problem, programmed no matter what the subscript is, you've got to type it, even if it's a 10. Any questions there? Now something like that, if that were on the test and you typed log 9 over 7, when you were reviewing the test, you better email me to point that out, because I'd go through and give you credit if you dropped the 10. But I have to know what happened, so here's another one. Write as a single expression. This is number 11. Nine log base 5 of z. 9 log base 5 of z minus log base 5 of z plus 1.
That's a 9 in front.
That's a 9. A 9 log base 5 of z minus a 5 log base 5 of z plus 1. Okay, let's see. Are we going to have a fraction bar in our final answer? Yes. I have a big smudge on these glasses, and I'm having to move all around to try to see around it. So, okay. So I'm going to write my log notation. Log base 5. And y'all said I needed a fraction bar because of what? That minus right there. Okay. What am I going to have on top? A z to the power 9, z to the power 9. On the bottom, z plus 1. Since that's all in the denominator, I don't have to enclose the z plus 1 in parentheses. They'd count it right if you did, but they'll also count it right if you don't include it. And notice there's no coefficient on that second logarithm, so no power on the denominator. Any questions there? So come back over here. So I type my log subscript 5, get out of the subscript position. Here's my fraction bar. On top I have z to the 9th And on bottom I have z plus 1. Any questions there? I think, hey, they just have log. And so since they don't show that subscript of 10, we should be able to type just an log. Okay, I typed my log. Do I need a fraction bar? Yes, I need a fraction bar. What's going to go on top?
Yes.
Okay, the 3x plus 5. Will I have an exponent on it? No, there's no coefficient. What's going to go in the bottom? X. Is there an exponent on it? Any questions there? Okay, number 13. Write it down. 1/2, is that a ln y plus an ln z? Okay, I'm going to write my ln. Do I need a fraction bar? No, there's no minus, so I'm not dividing. The only other thing, if you can't divide, what's the only other thing you can do inside there? Multiply. So you have y times z. Y times z. Well, wait a minute. Where's that 1/2 going to go? That's going to be, the 1/2 is the exponent on the y. That's the problem. Y'all need to vote. Y'all need to get together and vote to elect me ruler of the world. I'd be a very benevolent ruler, but I would first of all outlaw the use of variables that have curly tails on them. That'd be the first law. That would be the first law that I would pass, because it's hard to tell. That's what I've written there is ln, I have a y to the 1/2 times a z. Now Dale wanted to make that y to the 1/2 a square root of y, and that's perfectly fine. You can write it as ln square root of y with the z on the outside. But my lab will take it with the exponent of 1/2, so I'm going to leave it like this. I'm just going to type it there. Remember, when you're expanding, you have to convert those radicals to exponents. When you're condensing, if you're feeling lazy, you can stop with the y to the 1/2. That's fine to them. It's fine to me. So, heck, I'd like it better if these problems here started off, instead of the square root, if they started off with rational exponents. I'd like that better. I'm a lazy person, but you're not inclined to do that. So come over here. We're going to type in ln y to the 1/2. Get out of that 1/2 position. Get out of that exponent position before you type your z. Any questions there? If the logarithms are just being added, then you don't have division taking place. All that's occurring is multiplication. Number 14. I think this is one that I can do. Y'all tell me the answer. I'll give you a moment to write it down.
Is that a B?
Log base b, yes. I'll write my log base b notation. Log base b. First question, do I need a fraction bar? No, I don't need a fraction bar. Why? Plus we're adding. There's no subtracting taking place in front of those logarithms. So no fraction bar. That means we're going to be doing what to x and z? If we can't divide them, we're going to have to multiply. Well, x have a power of so what? Square, I agree. Get out of the exponent before we type. Z. Will the z have a power of so what? To the fifth. The pluses in the expansion do not transfer to pluses in your final answer. What takes the place of that plus? The multiplication. Number 15, I'll write this one down. Seven ln x plus 8 minus 7 ln x. You know, I've decided, I think I like condensing better because you only have to type the ln notation, the logarithm notation once. So, yeah, I think I like condensing better. I'll write my log notation. There's my ln. Will I need a fraction bar? Yes, because of that minus right there says the arguments will be divided. What will I have on top? X plus 8 to the power of 7. Anything else on top? No. What about on bottom? X to the 7th. Any questions there? So come over here, we type our ln, and then we need the fraction hot button. And on top, you have to have that x plus 8 in parentheses here, because that exponent of 7 applies to the entire x plus 8. Click down on the bottom, you have an x to the 7th. Is that what I wanted to type? Okay. Number 16. Five ln x plus 3 ln y minus 2 ln z. I'll write my ln. Will I need a fraction bar? Yes. What will I have on top?
X to the 5th and y to the 3rd.
Okay. X to the 5th and y to the 3rd. Not x to the 5th plus y to the 3rd. If this were a multiple choice problem, one of the distractors, the wrong errors, would be x to the 5th plus y cubed. And you'd be surprised how many people would choose it. Anything else on top? What about on the bottom?
Z squared.
Z squared, good. Like you don't show that minus. You don't show that minus in the expansion. That's replaced with that division bar. You don't show that plus, that's replaced with the operation of multiplication. Any questions there? Okay. ln. Back in the olden days, there were these things called mouse pads. Do they still make those things? I wonder why we don't have one here in this classroom. X to the fifth, get out of the exponent. Oh, we're still, oops, no, we're right here on top. No, there, y cubed, and on the bottom, we have a z squared. Is that what I wanted to type? Okay, dig out your calculators, if you have your calculator with you. I think we say on the syllabus, you need a calculator with a logarithm key, so let's look and find. If you're using one of these TIs like this thing here, I have two logarithm keys. I have an LOG and an LN. Find your logarithm key. And they want us to use a calculator to find the common logarithm. I said on the first day of class you need a direct entry calculator. That means you enter the step directly as it's typed. The first thing written here is LOG, so you click the LOG button. Uh-oh, there is a drawback to this big thing. It opened a parenthesis. Okay, you type in the 84, but then you need to make a habit. When they open a parenthesis, you need to close it. If it's the very final parenthesis and you don't close it, they're not going to count it wrong. But as we get the messier stuff we're typing in, you're going to have to be closing the parentheses. So make a note. If your calculator opens a parenthesis, you type that argument, then you close it using the close parenthesis key on your calculator. And they want it rounded to 4 decimal places. So that's a 1 point. Okay, 4 places. 1, 2, 3, 4. So that 42, is that going to stay at 42 or is it going to go up to 43? You look at the number after the 2. If it's 5 or bigger, these are traditional rules for rounding. If it's 5 or bigger, then it got round up. So that's a 9243. Any questions there? Those of you with your calculators, did you find your logarithm key, your common logarithm key? Now, if you have one of those, let's see, who has a Casio? Who has one of the little Casios? Is that a Casio? And FX, who is the, yeah, oh, I want to see something. Let me check something. Hold on. Let's see. Okay, let's see. I'm going to pause this a moment.